Let's take a moment to look at the big picture of what we've learned in quantum mechanics so far. So everything can be described by an element of a Hilbert space, which is basically just a vector space. Those elements in Hilbert space evolve forward in time according to Schrödinger's equation, which depends on the Hamiltonian. The Hamiltonian is just a linear operator associated with energy, which is Hermitian. All observables, which are operators associated with particular measurements, are Hermitian because they have real eigenvalues. The eigenvalues are the measurement results, which is why they have to be real, and the eigenstates of the observables are the states that the system will jump to if you make a measurement and you get that measurement result. And you can get the measurement probabilities from the second postulate there. So that's all from our previous courses in quantum mechanics, but we've reviewed that. We also had a look at different pictures. So previously you probably learned about the Schrödinger picture in quantum mechanics. You've also learned about the Heisenberg picture and indeed the interaction picture, and they're just different ways of breaking up expectation values and grouping the evolution either with the operators or the states. Now, still to come, we've made some progress towards, we want to finish today talking about symmetries and conserved quantities. The relationship between symmetries and conserved quantities is an idea that permeates all of physics, that we first discovered it in classical mechanics. We're about to discover it again in quantum mechanics, and indeed it becomes very important when we start talking about relativistic theories such as quantum field theory. After we talk about that, we're going to talk about vector operators and spin. Spin is one of the more counterintuitive things in quantum mechanics, and it's a good system to examine while discussing the ideas behind the transformations involved in discussing symmetries. We'll also then come back to another thing from classical mechanics, the idea of Lagrangians, and in fact you can formulate quantum mechanics using Lagrangians instead of Hamiltonians, and the action becomes a very important object in the what's called the many paths formulation of quantum mechanics. And so we'll see that those strong links between quantum mechanics and classical mechanics. And just to foreshadow that a little bit, it turns out that the principle of least action is actually an emergent property from quantum mechanics rather than something that's completely fundamental. And then after we've done that, we'll talk about some approximate methods in case you want to go on and actually make calculations in quantum mechanics. And ultimately, if you can't do calculations, the details of the theory will slip from your fingers and not be very useful. And so we'll talk about some ways to make those calculations viable and easy. So our discussion of symmetries and conservation laws led us to discuss how do you talk about a symmetry, and that of course requires us to talk about some kind of continuous transformation. And that led us to show that a transformation could be described by a unitary operator. And indeed, if you need a continuous set of transformations, then you need a set of unitary operators. And if they depend on continuous variables S1 to SR, R of them, then you've got an R parameter Lie group. And an R parameter Lie group has the identity, it has every inverse of every transformation in it, and there's always any pair of transformations that you do in a row leads you to another transformation still in the set. We did an example, which was the translation operator. You can see that it's a unitary operator here. It can take the state y and give you the display state y plus x naught. Let's show that this is unitary explicitly. So we did this, we showed that that was translation, and we never actually showed that it was unitary. So to show that this is unitary, we need to show that t of x naught times its Hermitian conjugate is the identity. So let's have a look at that. So we've got t of x naught. And now when I do the dagger, remember I'm going to have to choose a different dummy index. And when you take the Hermitian conjugate of operators, you turn all bras into kets and all kets into bras. You flip the order of all operators. So we're going to get, I'll use z. We'll get this flipped around and this flipped around. Okay, we can take the sums all the way through. And then in the middle, we're going to get yz, and yz is a Dirac delta function. So if we have a Dirac delta function, or indeed any delta function, that's good because it always allows us to get rid of an integral or a sum. I'll just get rid of the z, and so all z's turn into y's. And of course, we can just change variables by translating our variables because we're going from minus infinity to infinity, and so this is just... And from our completeness relation, we know that that is just the identity. So we have shown that this translation operator that we came up with last lecture is indeed unitary. And translations also have an unusual property for transformations, which is that they are additive, in the sense that if you apply two of them in a row, that's just the same as applying one of them with the parameters added together. This is a very useful property that doesn't always apply. See if you can think of a transformation that you know about that doesn't have this property.